Have you ever looked up at the night sky and wondered why the universe exists the way it does? Why stars twinkle in certain patterns? Why galaxies spiral in specific ways? Why time only flows forward? The questions we ask about reality often seem impossibly complex. Equations fill textbooks, theories contradict each other, and the deeper we dig, the stranger everything becomes. But what if I told you that the fundamental truths about our universe are actually far simpler than we imagine? What if the complexity we see is just our limited perspective, like a two-dimensional being trying to comprehend a sphere? Throughout history, the greatest breakthroughs in physics have come from deceptively simple equations. F equals ma, E equals mc squared. These formulas contain entire universes of meaning within just a few symbols. Today, we're going to explore three profound questions about reality using models that are simple enough to visualize, yet powerful enough to reshape how you understand existence itself. What is time? Why does the universe look the way it does? And why does light have a speed limit? By the end of this journey, you may realize that the universe you thought you knew does not actually exist. At least, not in the way you imagined. Let's begin with the most fundamental question of all. What is time? We talk about time constantly. We measure it with atomic precision. We waste it, try to save it, wish we had more of it. Black holes warp it beyond recognition. Gravity bends it like rubber. The James Webb Space Telescope peers through it to observe the ancient universe, 14 billion years in the past. But despite time's overwhelming influence on everything we do, what actually is it? You cannot taste time. You cannot touch it or see it or hold it in your hand. It has no mass, no energy, no physical substance whatsoever. Yet it pushes you forward relentlessly, whether you want it to or not. Every second that passes brings you closer to the future and farther from the past. You have no control over it. You cannot slow it down through willpower. You cannot reverse it. You are carried along by its current like a leaf in a river. This has puzzled philosophers and scientists for millennia. St. Augustine famously said, "What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I know not." Even one of history's greatest thinkers found time impossible to define. But modern physics has given us a clue. To understand time, we need to think about it in a completely different way. Time is not separate from space. Time is not something that happens to space. Time is another dimension. Now, before you think this sounds like science fiction, let's clarify what we mean by dimensions. In physics, dimensions simply refer to directions of measurement and movement. We live in three-dimensional space. You can move left and right, forward and backward, up and down. Three perpendicular directions, three dimensions. But what makes these dimensions special is that they are perpendicular to each other. They meet at 90-degree angles. This perpendicular nature is crucial. It's what allows us to measure space accurately and navigate through it without ambiguity. Now imagine a world with fewer dimensions. A two-dimensional being would live on a flat plane, like a drawing on a piece of paper. They could move forward and backward, left and right, but not up and down. Their entire reality would be confined to a surface. They could see the edges of other two-dimensional shapes, but if a three-dimensional sphere passed through their world, they would only see a circle that grows and shrinks. They could not comprehend the sphere in its entirety because they lack the dimension necessary to perceive it. Take this even further. A one-dimensional being could only move in a single line, forward or backward. That's it. their entire universe would be a single direction stretching infinitely in both directions. They could not comprehend sideways or upward. To them, such directions would be literally inconceivable. They might not even know they exist. Imagine being this one-dimensional creature. Your whole existence is a line. Other beings exist to your left or your right, appearing as nothing more than points. You cannot go around them. You cannot see past them. If something blocks your path, you are trapped forever. Photons traveling past this one-dimensional being would only be visible if they intersected the single line that defined their existence. Everything else would be invisible, existing in dimensions they cannot perceive. This brings us to an important realization. If we can imagine beings with fewer dimensions than us, unable to perceive directions we take for granted, might we be in the same situation? Could there be a fourth dimension that we cannot see, simply because we do not extend far enough into it? According to Albert Einstein's theory of relativity, there is. That fourth dimension is time. Einstein unified space and time into a single fabric called spacetime. They are not separate things. They are two aspects of the same reality. Just as there is no fundamental difference between the x direction and the y direction in space, there may be no fundamental difference between space and time. Time is simply another direction we are moving through, one we cannot see directly because we are too thin in that dimension. To understand how time works as a dimension, we need to build a model. And to build this model, we need to make a sacrifice. We need to compress reality. Imagine taking all of three-dimensional space, everything around you, the entire physical universe, and squashing it down into a flat, two-dimensional plane. This is not easy to visualize because we live in three dimensions, but mathematicians do this kind of compression all the time. They take complex shapes and project them onto simpler surfaces. So let's compress our three-dimensional universe into a two-dimensional plane. We'll call this plane space. It represents left and right, forward and backward, all the directions we can move within the physical world. But by compressing three dimensions into two, we've freed up the third dimension. And we're going to use that third dimension to represent time. Picture a graph. The flat horizontal plane represents space. The vertical axis pointing upward represents time. The bottom of the graph is the past. The top is the future. Everything in between is the present, constantly moving upward. In this model, a person exists as a two-dimensional shape on the spaceplane, a flat cutout, like a paper doll. As time passes, this person moves upward through the diagram. They rise from the past toward the future at a steady rate. As they move upward, they age. They are traveling through time. Now here's where it gets interesting. We cannot control our movement through time through willpower alone. We cannot simply decide to slow down our aging or reverse our direction. There seems to be some fundamental force or property of the universe pushing us forward through time at a constant rate, like a current in an ocean we cannot resist. However, we can change our speed through time by moving through space. This is where Einstein's relativity comes in. The faster you travel through space, the slower you travel through time. This is not speculation. This is measured, proven physics. Atomic clocks on fast-moving aircraft tick slower than identical clocks on the ground. When scientists compared them after the flight, the moving clock had measured less time. Astronauts on the International Space Station, orbiting Earth at over 27,000 kilometers per hour, age slightly slower than people on the ground. The difference is tiny, only a few milliseconds over months, but it is real and measurable. GPS satellites have to account for this effect. They orbit at high speeds, which slows their clocks down. But they are also farther from Earth's gravity, which speeds their clocks up. Engineers have to calculate both effects precisely, or GPS navigation would drift by kilometers every day. Our model can explain this through vectors. Imagine the two-dimensional person has a vector, an arrow, pointing out from their chest, showing their direction of travel. This vector represents their total velocity through space-time, not just through space. The length of this vector is always constant. It never changes. This is crucial. When the person is standing still in space, their entire vector points upward into the future. They are moving through time at maximum speed. But when they start moving through space, moving left or right on the spaceplane, something has to give. The vector can only be so long. If part of it now points sideways through space, less of it can point upward through time. The person is now moving through space, but at the cost of moving slower through time. Their clock ticks slower. They age more slowly. And if they were to move fast enough, approaching the speed of light, their vector would point almost entirely sideways. Almost all their motion would be through space, with very little motion through time. Time would nearly stop for them. At exactly the speed of light, the vector points completely sideways. 100% motion through space, 0% motion through time. This is the speed limit of causality. This is why light does not experience time. A photon emitted from a distant star billions of light years away experiences no time during its journey. From its perspective, it is created and absorbed in the same instant. From the perspective of the person traveling at near light speed, nothing seems strange. Their own vector, from their point of view, still points toward what they perceive as the future. To them, time is flowing normally. It is the rest of the universe that appears to have changed. Distances seem distorted. The stars ahead seem compressed while stars behind stretch out. But once they slow down and reorient themselves, once they return to moving primarily through time instead of space, it becomes clear that the rest of the universe has aged without them. Their twin sibling who stayed on Earth is now decades older. Entire generations have passed. This is the famous twin paradox of relativity, and it is absolutely real. This model predicts something else, something even stranger than time slowing down. As a person reorients their vector by traveling at high speed, their shape appears to change from an external observer's perspective. Imagine two people in our model, both starting out standing still in space, both moving purely through time. Their vectors point straight up toward the future. They appear normal to each other, two-dimensional figures standing on the space plane. But now, one person accelerates. They fire up a rocket engine and accelerate to 90% the speed of light. Their vector tilts dramatically, pointing almost entirely sideways through space. And as they do this, something strange happens. From the perspective of the stationary observer, the traveling person appears to flatten. They become compressed in the direction of their travel. The faster they go, the flatter they appear. At 99% the speed of light, they look like they've been squished by an invisible hand. At 99.99%, they're as thin as paper. At the speed of light, they would appear infinitely thin, like a pancake viewed edge-on, a line with no thickness at all. This is not an optical illusion. This is not a trick of light or perspective. This is a real warping of space-time itself. It is called length contraction, or Lorentz contraction, and it is a direct prediction of Einstein's special relativity. Objects traveling at relativistic speeds actually do flatten in the direction of their motion. But here's the truly mind-bending part. From the traveler's perspective, they do not flatten at all. They look perfectly normal to themselves. Their ruler still measures 1 meter. Their body still has the same proportions. Nothing has changed from their point of view. Instead, it is the rest of the universe that appears to warp and stretch. Distances ahead of them seem longer than they should be. The space between stars appears compressed. Objects rushing past them seem flattened. This is exactly what this model predicts. A two-dimensional shape reorienting itself in three-dimensional space would appear to flatten when viewed edge-on, but from the shape's own perspective, it is the rest of the world that has rotated. Now, in our real universe, we are three-dimensional beings reorienting ourselves in four-dimensional space-time. So instead of flattening in one direction like a 2D shape, we flatten in two directions. But the principle is the same. This model, simple as it is, accurately describes one of the strangest confirmed phenomena in physics. Particles in accelerators, cosmic rays from space, muons created in the upper atmosphere. All of these particles travel at relativistic speeds, and all of them experience time dilation and length contraction exactly as this model predicts. But this raises a deeper question. If we are flat in the time dimension, moving through four-dimensional space-time like thin coins tumbling through the air, what does that mean for our existence? Are we truly four-dimensional objects, or are we just three-dimensional slices of something larger? Now that we understand time as a dimension, let's tackle another profound question. Does space ever end? If you could travel far enough in one direction, would you eventually reach an edge? Would you hit a wall, a boundary, the end of everything? Or does space go on forever, infinite stars and galaxies stretching into eternity? To answer this, we need to understand the shape of space itself. And to do that, we need to talk about infinity. You probably know what infinity means. It's the concept of a number so large it cannot be beaten. Of course, no such number actually exists. For any number you name, I can name one larger. Add one to it. Multiply it by 2. Raise it to its own power. There is always something bigger. But that is the point. In infinity, there is always another number. Always more. The sequence never ends. When it comes to the universe, we have found no edges. Every time we build a more powerful telescope, every time we push back the darkness a little further, we find more galaxies, more stars, more space. The Hubble Space Telescope looked at what seemed to be empty patches of sky and found thousands of galaxies. The James Webb Space Telescope looks even deeper and finds galaxies that formed just a few 100 million years after the Big Bang. No matter where we point our instruments, we find more universe. So perhaps the universe is infinite. But what does that actually mean? What does infinite space look like? Surprisingly, there are multiple answers to this question. There are different kinds of infinity when it comes to the universe. There are 3 possible shapes the universe could have. Each one is infinite in a different way. A flat universe, a spherical universe, and a hyperbolic universe. Let's explore each one. In a flat universe, space extends in all directions forever, like an infinite grid stretching into eternity. Parallel lines remain parallel forever. Right angles remain right angles. Geometry works exactly the way Euclid taught it 2,000 years ago. Imagine drawing a triangle in flat space. The angles inside always add up to exactly 180 degrees. Draw a square, and all 4 corners are perfect 90-degree angles. For every light year you travel, you discover another light year of space. Simple, predictable, infinite, but in the most straightforward way. This is what the universe appears to be on small scales. When we look around us, when we measure distances and angles, space seems flat. Lines seem straight. Light travels in straight lines. Geometry is Euclidean. For all practical purposes in everyday life, space is flat. But this may be an illusion, caused by only observing a small piece of a much larger structure. It's like an ant on the surface of the Earth thinking the ground is flat because it cannot see the curvature over such short distances. The second possibility is a spherical universe. In this model, space curves back on itself, like the surface of a sphere, like the skin of a balloon. Try drawing two parallel lines on a sphere. Start at the equator, draw two lines pointing straight north, perfectly parallel to each other. You will quickly realize they are not parallel at all. They converge. They meet at the North Pole. On a sphere, parallel lines are impossible. All lines eventually meet. In a spherical universe, if you traveled in what you thought was a straight line for long enough, you would eventually return to where you started. Like a video game character moving off one edge of the screen and reappearing on the other side. You could circumnavigate the universe. With a powerful enough telescope, if light could travel freely without being absorbed, you could theoretically look in one direction and see the back of your own head. Light would travel all the way around the universe and return to you. This kind of universe is infinite in the sense that you can travel forever without hitting a wall, but it contains a finite amount of matter and energy. You just keep encountering the same objects over and over again. It is like being trapped on the surface of a planet. You can walk forever, but you will never escape. We know that spherical geometry exists in our universe. Black holes create it. Their gravity is so intense that it warps space-time into a closed curve. Inside the event horizon of a black hole, space becomes spherical in a very literal sense. No matter which direction you travel, no matter how hard you accelerate, all paths lead inward toward the singularity. You cannot escape. Every route you take curves back toward the center. This is spherical space taken to its terrifying extreme. Massive stars also curve space-time around them, though not as dramatically. The Sun curves space just enough that Mercury's orbit precesses slightly, shifting its orientation over time. This tiny effect, just 43 arcseconds per century, was one of the first confirmations of Einstein's general relativity. This curving of space is what we experience as gravity. Objects do not fall toward a planet because an invisible force pulls them. They fall because space-time is curved, and they are simply following the straightest possible path through that curved space. Gravity is geometry. Mass tells space how to curve, and space tells mass how to move. The third possibility is the hardest to visualize, but maybe the most important: the hyperbolic universe. In a hyperbolic universe, space curves the opposite way from a sphere. Instead of lines converging, they diverge. They spread apart exponentially. Drawing this is nearly impossible on flat paper because everything keeps getting wider and wider the farther you go. In hyperbolic geometry, if you draw a triangle, the angles inside add up to less than 180 degrees. If you draw a square, you can fit 5 of them around a single point instead of 4. Space itself has more room in it than flat geometry would suggest. What does this mean for the actual universe? In a hyperbolic universe, space itself is expanding. Not because something is pushing it apart, but because divergence is built into the geometry. Every point in space naturally moves away from every other point. Does this sound familiar? It should, because this is exactly what we observe. Every galaxy is moving away from every other galaxy. The universe is expanding in all directions at once. And not only is it expanding, the expansion is accelerating. Distant galaxies are receding faster and faster. Scientists usually explain this with dark energy, a mysterious force that makes up 70% of the universe and pushes everything apart. But what if the expansion is not caused by a force at all? What if dark energy is not a substance but a property? What if space is simply hyperbolic by nature? In a hyperbolic universe, the amount of space increases exponentially as you move outward. For every light year you travel, you discover more than one light year of new space. The farther you go, the faster space expands. It is like opening infinite doors, except behind each door are 2 more doors, and behind those doors are 4 more. The possibilities grow exponentially. This kind of infinity is larger, stranger, more vast than the infinity of flat space. Mathematicians call this uncountable infinity. There are more points in hyperbolic space than there are integers in all of mathematics. If the universe is truly hyperbolic, it means that given enough time, billions upon billions of years, every galaxy will drift away from every other galaxy until each one is completely alone, surrounded by nothing but darkness. The stars will burn out, black holes will evaporate, and the universe will become a cold, empty, infinite void. This is the heat death of the universe, the final fate predicted by thermodynamics. So, which shape is correct? Is the universe flat, spherical, or hyperbolic? Scientists have measured the universe very carefully, looking for signs of curvature, analyzing the cosmic microwave background radiation, the afterglow of the Big Bang itself. And what they find is that on the largest scales we can observe, the universe appears almost perfectly flat. The curvature, if it exists, is so slight that we cannot detect it. The universe could be a sphere so large we only see a tiny patch of it. Or it could be hyperbolic, but balanced against something else. But this creates a puzzle. If matter curves space into a sphere through gravity, pulling everything together, and the universe appears flat, then something must be curving space in the opposite direction to cancel it out. That something could be the natural hyperbolic geometry of space itself. Perhaps all 3 models are true in different ways. Perhaps the universe is hyperbolic by default, curving space outward, creating expansion. But mass and energy curve space inward through gravity, and these 2 effects balance each other almost perfectly, creating the illusion of flatness. This would explain why the universe appears flat, even though it is expanding. The hyperbolic expansion is real, stretching space itself, but gravity is pulling back, trying to slow it down. For most of cosmic history, these forces were nearly balanced. But as the universe expands and matter spreads out, gravity weakens. It has less grip, and the hyperbolic nature of space takes over. The expansion accelerates. This is exactly what we observe. For the first several billion years after the Big Bang, the expansion of the universe was slowing down. Gravity was winning. But about 5 billion years ago, something changed. The expansion started accelerating. Dark energy, or hyperbolic geometry, began to dominate. Now, we come to the final question, perhaps the strangest of all. Why does light have a speed limit? Why is it exactly 299,792,458 meters per second? Why not faster? Why not slower? Why is there a maximum speed at all? It seems arbitrary. We can accelerate a car from 0 to 100 kilometers per hour. We can accelerate a rocket to 11 kilometers per second to escape Earth. We can accelerate particles to 99.99% the speed of light, but we can never reach 100%, never exactly see. There is a wall, an absolute barrier that nothing with mass can cross. The answer may lie in combining everything we have learned: four-dimensional spacetime, hyperbolic geometry, and one very strange property of light. From an external observer's perspective, light always travels at the same speed. It does not matter if you are standing still or moving. It does not matter if you are flying toward the light source or away from it. Light always appears to move at exactly c, the speed of light. This is bizarre. If you throw a ball from a moving train, the ball's speed relative to the ground is the train's speed plus your throwing speed. Velocities add, but light does not work this way. Shine a flashlight from a moving spaceship and the light still travels at c, not c plus the ship's velocity. This has been confirmed by countless experiments. The Michelson-Morley experiment in 1887 tried to measure Earth's motion through space by comparing the speed of light in different directions. They found no difference. Light traveled at the same speed regardless of Earth's motion. But here is the truly strange part. From the photon's perspective, from light's own point of view, it is not traveling at c at all. It is traveling at infinite speed. This seems like a contradiction, but it is not. It is a consequence of time dilation. At the speed of light, time stops completely. Einstein proved this. If you could somehow travel at light speed from Earth to a star 10 light-years away, you would experience zero time passing. The journey would be instantaneous from your perspective. If we calculate your speed using the standard formula, speed equals distance divided by time, we get 10 light-years divided by 0 seconds. And dividing by 0 gives infinity. From light's perspective, it travels infinite distance in 0 time. It moves at infinite speed. So why does everyone else measure light traveling at a finite speed? The answer lies in the geometry of spacetime itself. Imagine spacetime as a four-dimensional hyperbolic geometry. All of three-dimensional space compressed into a two-dimensional plane, and time as the third dimension pointing upward. But now, space itself is hyperbolic. Lines diverge. Distances expand exponentially the farther out you go. In this model, imagine a massive expansion event in the distant past. A Big Bang. An explosion of space itself. This event sent everything in the universe moving upward through time at a specific rate. This rate of movement through time is what we perceive as the flow of time itself. Imagine that flow as a cosmic speed limit, a fundamental constant built into the fabric of space-time. Everything moves through space-time at this speed. Always. You cannot go faster or slower. The total magnitude of your space-time velocity is fixed, but you can change your direction. You can orient your velocity more through space and less through time, or vice versa. When you are standing still in space, all of your velocity points through time. When you move through space, you tilt your velocity vector, sacrificing time motion for space motion. Now imagine a photon, a particle of light. It is moving through this hyperbolic space at the maximum possible speed through space and 0 speed through time. Its velocity vector points entirely sideways. From its own perspective, moving through hyperbolic space means that distances collapse. What appears to be a vast distance to an external observer appears to be 0 distance to the photon. This is because in hyperbolic geometry, space expands exponentially. But from the perspective of something moving at the speed of light, that expansion collapses back to nothing. This is why light experiences no time and no distance. It is moving through a geometry where, From its perspective, all of space-time collapses to a single point. The entire universe, from the photon's point of view, is compressed into a single instant and a single location. Past, present, and future all exist simultaneously. Beginning and end are the same. But for us, observing from outside, watching the photon move through space-time, we see it traveling through normal space at a finite speed. That speed is c, 299,792,458 meters per second. The speed of light, the speed of causality itself, the maximum rate at which cause can propagate to effect. This is not just a mathematical trick. This may be the actual structure of reality. Space-time is hyperbolic. Light moves through it at what it perceives as infinite speed, experiencing zero distance and zero time. But because space-time itself is curved, because space expands hyperbolically, we measure that infinite speed as a finite constant. The speed of light is not arbitrary. It is a fundamental property of the geometry of the universe. What we have explored today is a model, a way of thinking about the universe that ties together relativity, quantum mechanics, geometry, and the nature of time itself. It is simple enough to visualize, yet powerful enough to explain some of the strangest phenomena in physics. Time is a dimension, not a river we float upon, but a direction we extend through. We are four-dimensional beings, moving through space-time like thin sheets tilted at an angle. We do not extend far into the time dimension, which is why we cannot see it directly, cannot perceive past and future the way we perceive left and right. We only experience time as the relentless flow from past to future, from birth to death, from creation to entropy. Space is hyperbolic. It curves outward, naturally expanding, creating the acceleration we attribute to dark energy. But mass curves it back inward, creating gravity, the attraction between objects. These forces balance delicately, making the universe appear flat, at least for now, at least in the small patch we can observe. And light moves at the speed it does, because it is traveling through this hyperbolic space-time at what it perceives as infinite speed, experiencing no passage of time, no sense of distance. The speed limit of the universe is not imposed from outside. It is built into the structure of reality itself, woven into the fabric of space-time. These ideas may seem abstract, disconnected from everyday experience, but they are grounded in real physics. Einstein's relativity, confirmed by GPS satellites and particle accelerators, observed time dilation, proven by atomic clocks on aircraft, the expansion of the universe, measured by the redshift of distant galaxies, the constancy of the speed of light, tested in countless experiments over more than a century. All of these phenomena fit together into a single, elegant model. The universe is far stranger than it appears, but it is also far simpler. The great truths, as always, are simple in their final analysis. We just need the right perspective to see them. But what does this mean for us? For our existence? If time is a dimension and we are flat in it, does that mean our past and future already exist somewhere? Are we like frames in a film strip, each moment already laid out, just waiting to be experienced? Some physicists believe this. They call it the block universe. In this view, all of time exists simultaneously. Past, present, and future are all equally real, all part of the same four-dimensional structure. We simply move through it, experiencing one moment at a time, creating the illusion of flow. If this is true, then everything that will ever happen has, in some sense, already happened. Your birth, your death, every choice you will ever make, all of it exists right now in the four-dimensional structure of space-time. Free will becomes an illusion. You are not choosing your future, you are discovering it. But others argue that this is too deterministic. Quantum mechanics, they say, introduces true randomness into the universe. The future is not fixed. It is probabilistic, constantly branching into multiple possible outcomes. Time does flow. The future is genuinely open. We do not know which view is correct. Both are consistent with everything we observe. Both explain the same phenomena. The universe does not tell us which interpretation is true. But regardless of whether time is an illusion or a fundamental flow, regardless of whether the future is fixed or open, one thing is clear. The universe you thought you knew does not exist. Not in the way you imagined. You are not a three-dimensional object moving forward through time. You are a four-dimensional structure, a thin slice of space-time, reorienting yourself as you move through the cosmos. Your past, your present, your future may all exist simultaneously. Different slices of the same higher dimensional shape. Space is not a static backdrop, an empty stage where events unfold. It is a dynamic, expanding, hyperbolic geometry that curves around mass and stretches between galaxies. It has shape and structure and properties of its own. And light does not simply travel fast. It moves at infinite speed through a curved space-time, appearing to us as a finite constant because of the geometry we inhabit. The speed limit of the universe is not a rule imposed from outside. It is an intrinsic property of reality itself. These ideas challenge everything we thought we knew about existence, but they also reveal something profound. The universe is comprehensible. Despite its vastness, despite its complexity, despite billions of galaxies and trillions of stars and incomprehensible scales of space and time, the fundamental structure of reality can be understood with simple models and elegant mathematics. We live in a cosmos that makes sense, a universe governed by rules. And those rules, strange as they may be, are within our ability to grasp. This is the universe as it truly exists. Not as we perceive it through our limited senses, not as it appears from our constrained perspective, but as it actually is. A four-dimensional hyperbolic space-time, carrying us all forward into an ever-expanding future. And now, you know. You have seen beyond the illusion. You understand that the universe you thought you knew does not exist. But in its place, you have discovered something far more fascinating. A reality stranger and more beautiful than you ever imagined. The question is, what will you do with this knowledge? How will it change the way you see the stars, the way you experience each passing moment, the way you understand your place in this vast, expanding four-dimensional cosmos? The universe does not exist the way you thought, but it exists nonetheless, and you are part of it. A conscious pattern of matter and energy, moving through space-time, observing and understanding, asking questions and seeking answers. In a universe that does not have to make sense, we have found sense. In a reality that could have been chaos, we have discovered order. That is perhaps the greatest mystery of all.